Yeah, let me just start by, let me explain from here the partial sums. Because the integral test is that one everyone can understand. So, yeah, so this is what I said, right? So I say that if we're given this series, then we can expand it to be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on, right? And then now we say that if I'm gonna have to take these partial sums, I'm going to be focusing on the base 2. So what I said is that I'm gonna be focusing on the base 2, which the base 2 will be, if I start here and say, remember I said that these are sequences, right? These are sequences Sn. So if I'm going to take these are going to be my partial sums, right? Sn. So I said that those partial sums Sn do have this the sub sequences, you see, right, that I can take. So I said that for us to combine the two theory without having to go learn about the subsequences, we're going to say we consider the base 2. We're going to consider base 2, and I say that we're going to have S2, we start from 0, this will be S1, and then S2, 1, this will be S2, S2, 2, this will be S4, then S2, 3, and this will be S8, and then we come to S2, 4, this will be S16, up until S2 to the n, right? So if we have this, now we can agree that I can come here and say, since this is my S1, I'll take it as this, right? And since this is my S2, I'm going to take this 2, S2, S3, I'm going to take this 3, S3, S4, I'm going to take this S4, right? But on this part, I'm only going to include these ones, right? Because I'm going to be looking for Sn, S2 to the n, this one. I'm looking for this subsequence. So if I get this subsequence, I need to know what is this subsequence equals to, so that I can deduce whether it is converging or diverging. So I'm going to take the limit at the end of this. You see, right? Also the limit of this side. So what now I should do is I'm going to say, yeah, let me do this. I can erase this, right, and then I'll write it. So what I can do now, I can say this. I can say that I'm going to take the partial sums S1, which will be this one, and it's coming from this part, right? I'm taking S1, which will be 1. Then the next one which I should take is S2. Is that right? Then I'll take S2. So that S2, this will tell me how many elements to take from there, right? I'm going to take 2 elements. Then this will be 1 plus 1 over 2, right? And then now I come and say, so now everything that is not of base 2, if I find something that is not of base 2, if I have anything plus anything that is not of base 2, then I must say this, I must say manipulate this using the inequality sign and change that thing to be base of this one, right? So we can say that on the next one. So we know that after S2, we're supposed to take S4. So I'm going to have S4 is equal to 1 plus, I take 4 elements, right? Which is 1 plus 1 over 2, 1 over 3, plus 1 over 4. You see, right? Then I said that if I have anything that is not S2 here, I must change it to be, if I have anything that is not of base 2 here, I must change it to 1 over 4, you see. And that means that this is going to be greater than 1 plus 1 over 2 plus 1 over 4 plus 1 over 4. You see, right? And then this will be 1 plus 1 over 2 plus 1 over 2. If I add 1 over 4 plus 1 over 4, I'll get 1 over 2. You see, right? Then the next one after 1 over S4 is S8. Then I'll get S8 is equals to, so this one means that I'm supposed to take these elements from 1 up until 8. You see, right? This one, it was 2. I took it up until 2. This was 4 up until 4. So now I'll say 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. Now we check this, right? From the previous part, we had that 1 was alone, then these ones are 2, right? So these ones are not the problem because this is a base of 2. This one is a base of 2 to the exponent 0, right? And then this one here, we're supposed to change this one, right? So this was the part which was affected. And if we come here, whatever part that was affected, we're gonna put it in brackets alone. Then the second part, we'll put it alone also, all of it. You see, after this part. So I'm going to say here, this will be greater. Now check this. This was changed to 1 over 4 previously. So we should change it also here to 1 over 4. And these ones here, I said that if they're not of base 2, they will be changed to over this. You see. So we're going to change them and say 1 plus 1 over 2. These ones were changed to 1 over 4 plus 1 over 4. You see, right? Plus, then this will change it to 1 over 8, all of them. Plus 1 over 8, plus 1 over 8, plus 1 over 8. If I add these 1 over 8 plus 1 over 8, I'll get 1 over 2. So this will be equals to 1 plus 1 over 2 plus 1 over 2 plus 1 over 2. You see, right? So in other words, for every sequence, or for every partial sequence, I'm adding 1 over 2. Check here, I had 1, then the second one I added 1 over 2, I added 1 over 2, I added with 1 over 2 also here. You see, right? So this will be the case, the same case with the one which is coming next, which is S16. After S8 is S16. Then we're going to have S16 to be equals to 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. So let me write up until 8, right? Plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. Then from here, I'm just going to write 1 over 9, 1 over 10. Then I do this because I can't write all elements. I know that it should end at 1 over 16. So I come and check. There, here we had circled, we had put this inside brackets, 1 over 3 plus 1 over 4. Then we had put 1 over 5 up until 1 over 8. That means that the remaining will be in its own brackets. You see? Then this will be, we're going to have this will be greater than 1 plus 1 over 2 plus 1 over 4 plus 1 over 4. You see, right? Plus this changed again to 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8, because the highest here is 1 over 8, you see, in this bracket. And then plus the highest in this bracket is 1 over 16, so we'll change it to 1 over 16 plus 1 over 16 plus 1 over 16. So I know this will be 1 plus 1 over 2. This one becomes 1 over 2. This one also becomes 1 over 2. And also the last one also becomes 1 over 2. If we can check, the last one we had 3 1 over 2s. This one it must have 4 1 over 2s. You see, right? So this is the case. Then the last one, we're going to say, now we have S, I think before we come to that S of what we can stop here, right? Then let's check this now. Now let's try to associate, because now we're computing this one, the right hand side, right? Now we can compute the left hand side. We're computing this side. Now let's compute this left hand side. So now we can see, now let me do this. Okay, Now we can say that this is the same thing as having. Now we can say this. We can say we observed that as the first one was what? S2 to the 0, right? S2 to the 0 was it greater? Yeah. No, it was equals to 1. S2 to the 1. This was greater than 1 plus 1 over 2, which is this one. S2 to the 0 is this one, right? And then S2 to the 2. So it's much preferred. Even this one we can write greater or equals to. The first one we can write greater or equals to. Then the ones from there we write just greater. So it's preferred that we write like this. Then S2 to the 2 is S4, right? It was 1 plus 1 over 2 plus 1 over 2. 1 plus 1 over 2 plus 1 over 2. Then we had S2 to the 3, which is greater than 1 plus 1 over 2. 1 over 2 plus 1 over 2. You see, right? And also we had S2 to the 4, which is greater than 1 plus 1 over 2 plus 1 over 2 plus 1 over 2. Then I add the last one, 1 over 2. And then now we can say, since we have these, right? Now we can say that S from this part, right, from S to the 2, 4, and then we can have S2 to the n. S2 to the n, we can have S2 to the n. S2 to the n, which S2 to the n will be the same thing if I say greater. Then I'm just going to have 1 plus, then I can have 1 over 2 plus 1 over 2 plus 1 over 2. Then we don't know how many times these 1 over 2s will go. You see, right? Check this. Now I want you to check this. Here was exponent 0. We had the 0, 1 over 2s. You see, it exponent 1, we had 1 over 2. Then we had exponent 2, we had 2 of them. Exponent 3, we had 3 of them. Exponent 4, we had 4 of them. So it means that exponent n, we should have n of them. You see, right? So this will be like that. So it means that we can now come and say the limit as n approaches infinity of s to n, which will be equal to the limit as n approaches infinity of 1 plus n over 2. And this side will be the limit as n approaches infinity, and this will be 1 plus the limit as n approaches infinity of n over 2, and this would be infinite. You see, right? So it means that we have shown that this thing is divergent. So we're good to go. Any question? Any question? Did you guys were asking a question? Oh, guys, can you please type the questions, because I can't hear them. I've muted you guys so that I don't hear you. Because someone I think was receiving some noise. If you are speaking, then I speak. The what's this? The mic sometimes gets interrupted. So let me just turn on my sound, right? Then you can speak. If you are asking a question, you'll speak. Yeah, I see it. Yeah, I received some question. Yeah, is there anyone who was asking a question? If you're asking a question, please, you can raise your question again, because I couldn't hear you that time. Anyone was asking a question? We have a few seconds before we proceed. Anyone asking a question? All right, I'm going to skip. If you have a question, just tap there. But by any luck, I can view and check. Right. So yeah, let me just turn off the sound. I can't hear you again. If you ask a question, I can't hear you. You can see now I'm turning off the sound. So I can't hear you. Yeah, just make sure you type there, guys. So now I think the part of harmonic series we have concluded it. But if there's if there's any question, I wanted also to look at the P series, using the P series to solve the harmonic, but we will have to go through the P series first, right? So that we can see how the P series is computed. So also we're gonna go through some parts that we went through before. So I think those parts we did them on sequences, but now we're gonna have to do them on this part of series, right? So let me try to open this. I'm trying to open the Google Meet. So yeah, I think now I've opened the chat box there. If you're asking something, I'll be able to hear you. If you ask something, I'll be able to hear you. I opened the chat box. Yeah, please, if you ask something, I'll be able to hear you. So yeah, I think now it's fine. Yeah, I'll be able to see one, not hear. So I'll be able to see what you'll be asking. So yeah, now since we're done, I'm gonna send you guys some questions, right? Based on the telescoping. Badly we can't do them. I wish we could, but we won't have time, right? So we're going to look at test for convergence, because there we were looking at harmonic, and we did consider the integral test. So when we look at test for convergence, we're going to be looking at the integral test. We also look at the P series. So by any chance, we can look at the test for divergence. So now for the test for convergence, we can look at this as saying that we can test whether a sequence or a series, for this case it's a series, we can test if a series converges or diverges. That's how we're going to look for the test for convergence, right? We can test using different methods or different tests. So the first one that I want us to look at is the integral test. Even though we have used the integral test there, I want us to discuss it in detail. What do we mean when we talk about the integral test? So based on the integral test, right, let's suppose that I'm given a series, right? I'm given a series of I of n, from which n is from 1 up until infinite. So we're going to say that this series, we're going to say that the series is convergent if and only if the improper, so you saw that there we use the improper integral, right? The improper integral, so we can have it from a to b of f of x dx converges. Yeah, converges So otherwise it is divergent, right? So now let's look at the two conditions. So, or let me just maybe give this a b variables, because here it's moving from 1 to infinity, right? This is 1 to infinity, okay, based on this. So now if we look at two conditions, right? So the two conditions that we have is, I'm going to first discuss the one which I wrote here. So I'm going to say that if we're going to use the integral test. If we're going to use the integral test from 1 to infinity of f of x dx, this is how we're going to conclude, right? If this is convergent, so this is part of the way that we're going to conclude, not exactly this statement, but this is what we should know always. Then this is let me say convergent. So if this integral is convergent, the improper integral is convergent, then the series of a of n will also be convergent. So always you must note that this is an improper integral. If you integrate it in other ways, you're in danger. You're going to get 0. So again, if we say that this same integral of f of x dx, don't forget, even though it's a test for convergence, I said that when we talk about the test for convergence, we're saying that it is either converges or diverges. So that's what we look at, right? So if this is divergent, then the same series, so when we're checking harmonic series, we found this, right? The same series is divergent. You see, right? The same series will be divergent. And then, yeah, there's no question, right? If by any chance you ask a question, I'll see it. So using this, we can be able to solve any type of question, right? So now let's go back to that question that we had. So we had the question, this from harmonic r was 1 over n. And I said that, okay, but it's fine, I don't have to write those. So I said that since we solved it we checked using the integral test first, then secondly, on the integral test, we usually integrated, right? So let's go back and check. We integrated, which is this. We integrated and found infinity, found that this thing diverges. But there's also an easier way than this, right? Which is the p test, the p series. So what we can have here is we can first discuss the p series, right? So when we talk about the p series, you should know that here we have a p, is it right? The p series. So the p series is like that. So for the p series, we should know that we have two conditions which we can say that this will converge. But before it converges, let me say that this is associated. This will be associated. So here we're going to associate it with the but I don't have to write what is it associated with. It's fine. Because we see, again, I'm writing it on the integral test. So I don't want to write what is it associated with, because some can confuse it, right? Because we're not only going to use it on the integral test. We are also going to use it on other parts, right? Also the comparison test. So not greater or so, it's greater than 1. Diverges right. So this is what we should know about the p-test. So given that if we change this here in this case, if we let f of x to be equals 1 over x to the p, then we should know that this will occur then the above conditions are true so they will be true for the part where x is an element of 1 to infinity, right? Because we replaced n by x. This one was supposed to be infinity, right? Supposed to have written infinity here. Here I should have written infinite. I don't know why I wrote n, because it's infinite series. So this will be the case. So let's now look at that question, right? Let's now look at that question. If we have up until infinity, and if we have this, we can use the p-test here. So the question is, how will I use the p-test, right? So for me to use the p-test here, I must let, so I'm going to first let f of x to be equals to 1 over x for, so it's either this, I say this is an, I can, but as we're using a of n, right? For a of n equals to 1 over n. You see, some from the guide you can use f of n, you can use that, some they use a of n. So, but I prefer this one that you're using, but it's fine, n is fine, you can use n. So this will be the case, right? Then, now we know that we're going to have the integral from 1 to infinity of 1 over x dx. So now we're checking the improper integral dx, you see, right? So now we're saying that since p is equals to 1, let's check what happens when p is equals to 1. Diverges, and then the improper integral diverges by p series. You see, right? So the improper integral will diverge. So is there any question? But I can see no one is typing anything on the chat box, so it means that there's no question. So now we say this, right? So let's come and check the test for divergence. But this is the condition that I can write note or NB. We should note that, so this will be used, usually we use it in, I think it's the alternating test. So when we come to alternating test, we'll discuss it more. But we should keep in mind that if the series from 1 up until infinity, which is an infinite series, then we say that converges. If this series converges, And then the question is, what is the limit? And then I can say the limit as n approaches infinity of a of n will be equals to 0. So let's try to find the limit of this. The limit of this will be 0. You see, right? So if it converges, but this one does not converge, so it's not always the case. This is just a lemma that is there. So here, that's what they didn't say if the limit is 0. They said that if the series converges. So we start with the series. It must converge before we decide this, right? So if it converges first, then we'll say that a of n is equal to 0. So if we are going to test for divergence, then we're testing for convergence, right? If we're going to test for divergence, then we should know that this is not supposed to exist. We can say that if the limit should not exist. Remember from the sequences, you were finding the limit first. If you find that it does not exist, then automatically you know that that sequence diverges. Then if you found that it exists, then you can prove that it converges. You see, right? And so that if the limit does not exist, or the limit is not equal to 0, or the limit as n approaches infinity, let me say it's not equals to 0, then this series I of n diverges. You see, right? Then this I'm just writing the definition because they can say define it. You see, right? And from sequences we had this. We had these theorems from sequences. We had these theorems from sequences. The first theorem was that if you're given that we have the limit of a of n and b of n, right? And they're equals to L and M. So in this case, there we had the limit as n approaches infinity of a of n. Let me say, not really a of n, let's say, C a of n. This will be C, the limit as n approaches infinity of a of n, which we know that the limit of a of n is L, right? Then this will be CL. You see, right? So this will be the case. But when we come to this case here, we're going to erase the limit. Then we'll write the summation. You see, right? We erase the limit. We'll write the summation. So I'm going to write the summation. Then I erase this. I don't need this anymore because now I'm not finding for the limit of the sequence. You see, then this will be the case. Then for the second one, we can have the summation of n equals to 1 of a of n plus b of n. Then this will be the summation n equals to 1 of a of n plus the summation n equals to 1 bn. You see, right? Then again, if we have this summation of infinity n equals to 1 of a of n and b of n, and this will be the summation infinity n equals to 1 of a of n times the summation of infinity n equals to 1 of b of n. So This is what we can have, right? So if we have this, then we know that we can be able to find this. So we're not gonna do this now. So I can just put a star here. You can also try to check them in the guide, then we'll come back for them. So now we're doing what? We're doing the test for divergence, right? Then the p-test. Okay, so but for the p-test, I only showed you one example, right? But you know that if this was squared, if this was squared, you know that this will be 2. And if it's 2, it will be falling under the convergence part. So you're just going to do the opposite and say that then the improper integrals converges. You see, then by p-series, okay, I didn't finish this statement. I think I did well going back. So you know that this diverges then by p-series, the series diverges. You see, right? So if p was 2, means that we're only gonna change this to converges. You see, right? Then we would also know the limit. The limit would be 0. So it would be simple for us to know the limit, because the limit of that thing would be 0. We agree, right? So now let's look at what else. Do you have any question on p-test, guys, before we can move to the next part? Any questions on p-test? Any question? So there's no question, right? Alright, it's fine. So now we come to comparison test, right? Now we come to comparison test. We have comparison test. We have comparison test. So last time we discussed about comparison test, so I think we can, but it's fine. Doesn't for us to go back. So we discussed about comparison test, and also we discussed about the limit comparison test. Everything is still the same thing. Everything's still the same. We just need to now remove those limits and put the summation as I showed you on this part, right? So it means that now if we suppose that we are given the series of A of n and the series of B of n, right? If we are given this series of A of n and B of n, then we can say, and this we are supposing that this should be greater than 0. So this should be greater than 0, right? So we're going to suppose the reason why they should be greater than 0 is it's for comparison test. We focus on the increasing the increasing sequence or series. So we can say now that if the summation of the summation of n from 1 up until infinity of bn, so this will be the second limit that will be reduced zenith 2. So bn will be the second limit. So I'll show you an example. If I have n squared plus 1, then I say that this will be less than 1 over n squared. This will be a of n, and this will be b of n. So you see, so I'm saying that since we'll be computing using this, or we'll be checking using this, you see that this by p-test would converge, right? So saying that if b of n converges, you see, and this is less than or equal to this, you see, right? That's the second condition you should be checking. Is this true? If yes, then does this converge? You see, then if yes, then this a of n is also convergent. So let's write it here. Let's write it here. So remember I said this, said we have A of n less than or equal to B of n. So the first question we ask ourselves, is this convergent? Is that right? Is this convergent? If yes, if B of n is convergent, right? And the second question you ask yourself, is B of n greater or equal to A of n? You see, and A of n is less or equal to B of n. You see, then A of n will be convergent. Is that right? And the summation from 1 to infinity of A of n is convergent, or is also convergent. You see, right? Then this will be the case. Then let's now say, okay, let's say now the limit decreases, you see, because initially would focus on increasing limits. So I remember there was this other question in the tutorial that when we were reducing, you remember when we reduce, most of the times we say this, right? But that question, when you reduce, you're supposed to go this side, not this side, you see. So now I would say that the second condition, I'll just put this in red, right? We're saying that now, if it happens that we find that now, let me write it like this. That's fine, right? Yeah. We find that now B of n is on the left hand side. You see, find that now this is decreasing. You see, it's on the left hand side. For this one, I can say increasing. Series. So if the series, now it happens that it's decreasing, right? Then, why did I erase this thing? Let me write it down here because I want space. B of n. You see, right? So you're gonna first ask yourself a question, right? We find that it is what? It is increasing, right? Or it is decreasing, not increasing, it is decreasing. Then we ask ourselves this question. Then I'm gonna first ask myself and say, if now this, if the sequence, so if the summation, so some guides they write if the summation of B of n, of A of n, right? So let me check what does use, right? Because on this one some they write if A of n is divergent, right? Then some they write if B of n is divergent, which for B of n it will be the most reasonable one. So let me just check which one do they write on this guide. Let me just do this. I'm gonna log in on my Blackboard and then I check it there. Or is there anyone who can tell us what does your guide write? Those who have looked at the guide. Those who looked at the guide. Not usually if I gotta see you have many lecturers, right, for different classes. So some they can look at this part and then some they look at this part, then they come and show you different. It happened last year. They come and show you different ones. Then the ones that will be safe are the ones that their solutions are the same as the one in the guide. So you should always make sure that you confirm with the guide. So let me just check the infinite series. That's what. Comparison, right? Comparison test. Yeah. So they take the most reasonable one. So also them, they took the same thing. Given that now, yeah. You see, then we have So the one that is in the slide they made a bit of a mistake there. So you should go, if you're using those slides which are sent there, you should go and rectify this thing. So if the summation of this, because initially we're given A of n, right, and it's decreasing, so we reduce going down. So the reasonable one to take is B of n. So if B of n is divergent and B of n is less than or equal to A of n, then it would mean that the summation of n from 1 to infinity of A of n is also divergent. You see, right? It's also divergent. So this would be a very nice explanation to this. So it means that now we can choose any question and try to check how does this work, right? So we can choose any question. So let's say this. Let's say we have the first example. We say that now we're given say test the series. So if they give us and they say we should test the series summation n to 1, n from 1 to infinity of 1 over n plus 2. You see, this question can be solved even though even though this question is for telescoping, right? You can still use it you can still use another method, right? Comparison test. So now we can say this. We can say that I have this first, right? I'm given this. So since I'm given this option, I can let A of n be the original one, the summation. So this will be or maybe let me say this will be 1 over and now I'm not going to use the summation because I want to follow this definition. So it says Bn A of n, so it shows that we must take them independently. And then and this would be what? This would be 1 over n squared plus 2n. You see that? So we ask ourselves, right? We want to know between the two conditions, two definitions. We want to know whether A of n will be less than or equal to Bn. This is for increasing, or A of n will be greater or equal to B of n. This is for decreasing, right? So I want to know. So this one I like to put B of n first. I want to know this. I'm going to plug values. If I plug 1, I'm going to get 1 over 3. If I plug 2, I'm going to get 1 over, what will I get? 1 over what? 2 is 4 plus 4 is 8. Then if I check between 1 over 2 and between 1 over 2 and 1 over 8, which one is big? 1 over 3 and 1 over 8. Or let me do this first. No, that's fine. If I check it like this, it's gonna be a bit difficult for us to check. It's fine. We can opt for the second opportunity. I think we can say this, right? Since we have A of n, we can check it like this. We can say our A of n is 1 over this. Then we say B of n. If I was going to reduce this, right? First, let's start by reducing it, and now we say fit, right? We can have this. We can get rid of the non-dominant one. You see, right? Which is 2n, it's the smaller one. So let's check here. If I plug 1 here, I say that I'll get 1 over 3, right? But if I plug 1 here, I'll get 1. And which one is bigger? Bn is big. If I plug 2 here, I'll get 1 over 8. If I plug 2 here, I'll get 1 over 4. Which one is bigger? Bn is bigger. You see? So I think this way it will be much simpler than to check 10 by 10. So now we see that we can take this. So it means that we must now come and say, this is what you must say in the rule. You must say that 1 over n squared plus 2n will be less than 1 over n squared, right, for all what? N. Then you come and check what is Bn. Is it convergent or not? So let me erase here and write that. So we know that we are going with this one. So let me show you how we're going to write the solution. So we let a of n be that, and also and b of n be equals to 1 over n squared, right? And then we want to apply the condition. First thing that we can check is a of n less than b. Yes, we did check that, right? Then we know that a of n is less than b, and a of n is n plus 2, which is less than 1 over n squared. Is it right? For all what? N. So in other words, for all n element of natural number. And after that, we should check whether this converges or diverges. You see? So we say and, but usually in this case, it should diverge as long as this condition holds. So we say that and. Now we have this, the summation. We should check the summation of Bn. If we come back here, so that if the summation of this is convergent and this happens, therefore a of n is convergent, the summation of that, right? So first we have this. Now we must check for this. So we're going to check, let's say the summation. This is 1 over n squared. You see, so there's no need for me to change this to integral test. So I can say that this is convergent. I can say that this is convergent. So by P series. You see, right? Which this would imply. You see, then is the same thing as imply. It would imply. The question is, what would it imply? So this would imply that the summation, we're not talking about the summation of a of n, right, of 1 over n plus 2 converges by comparison test. You see, right? So that converges by comparison test. So any question on this? Any question? Let me check if anyone is asking a question. Any question on this? Alright, seems like no one is asking a question. So since no one is asking the question, we can proceed. So now we look at the limit comparison test. The limit comparison test. The limit comparison test. We look at the limit comparison test. So if we can ask ourselves about the limit comparison test, we also applied it last time. Remember we did this last time, right? I think we discussed the limit comparison test last time, and then we managed to get to some conclusion, right? So if we look at the limit comparison test, also we're going to suppose the same thing as a comparison test. We're going to suppose that if we have the summation of a of n from 1 to infinity, and again we have the summation of b of n from 1 to infinity, then we can say, and then remember I said that here we're dealing with them being positive, right? So now we say such that for the limit comparison test, we should check a of n over b of n. Is that right? So this will approach a certain variable which is non-zero. So we'll approach a certain value as n approaches infinity. You see, right? And such that L is not equal to 0, or L is not equal to infinity. You see, right? So this will be the case. Then if this happens, then we can say, we can say that either one of these diverges or converges, right? We can say either the summation infinity n from 1 a of n and summation n equals 1 b of n, they both converge. They can either converge or diverge. You see, they either both converge or both diverge. You see, right? So this will be the case. So here we can also try to prove this, right? We can also try to prove this and see where it can lead us. So, but we'll do the proof. It's not that difficult. We're just gonna take. We already have this. We know that we should take this out to the other side and start to solve that. So let's say we're given an example now, right? We have an example. So let's say we have an example. Now we say that we're given. Let's say we're given. We can be given what the summation, right? We're given the summation n from 1. Let's use the same thing. We had n plus 2. But remember that this one was converged, right? Using the comparison test. Let's say now I'm going to use the limit comparison test, right? For the same question. So I'm going to let, again, same approach, a of n be equals to 1 over n plus 2, and I let b of n be equals to 1 over n squared. You know how we came about this, right? For all n. See, but for all n, we'll write it, we're not comparing that. But here we're not comparing, it's fine. Then we say that already, remember that I said that they should both be greater than 0, right? So that we know. So we can say, and a of n is greater than 0, and b of n is greater than 0. Then we say then, now the condition says that if this is true, now we should check what is the limit of a of n over b of n. So we now have, let's start by checking a of n over b of n, then we'll check the limit. Right? So we know that a of n is 1 over n squared plus 2n over this is 1 over n squared. And this would be n squared over n squared plus 2n. You see, right? So this will be the condition. So if this happens, that we get this, we're going to compute its limit. And what will be the limit for this? 1, right? So yeah, but let me show you how did we get this one. So if I factor out n, I'll have the limit as n approaches infinity. So you have reached that level where we say you have grown, right? Some things you see them. And this will be 2 over n. So if I factor out n squared, this will be 1. Then this 1 over n squared, n will cancel n, I'll be left with 2 over n. You see, right? So that is the case there. And this will be 1. You see, because this will be 0. So now we get 1. So we come back. The condition says that we should get any number, but that number should not be 0 or infinite. You see, right? So if that number is not 0 or infinity, now let's go. Now we must deduce, right? Now we can say, now the summation of n equals to 1 of a of n and b of the summation of b of n either converges or either both converges or both diverges. All right. So now the question that we should ask ourselves is it converging or diverging? But the only way to check that is if we go back to comparison test. You see, right? If we go back to comparison test, we check is a of n less than b of n. Then if that's the case, you can come back here and say b of n. You see, since here b of n is greater than a of n, we can come and say thus, you see, then I say the summation of n, I check b of n. We always check b of n. You see, right? I check b of n is convergent. You see, we say that it's convergent by what? By p series. Because p is greater than 1. You see, so by the limit comparison test, also the summation of 1 over n plus 2 also converges. You see, right? So that is the case for the p series test. So is there any question? The limit comparison test using the p series. That is the case. Any question? So there's no question, right? Oh, let me check. Anyone asking a question in the chat box? No. So now we ask ourselves, right, that let's say this was equals to 0 or infinite. What would happen? Obviously this would diverge. You see, right? So automatically this would diverge if that was the case. So this would diverge. So now let's go to the next one that we have is the alternating series. Then I think let's start with the ratio test, right? So let's start with the ratio test. Oh yeah, I think, but it's fine. We can start with the alternating test. The alternating series. So the alternating series, we most of us, we are familiar with this. I can say all of you are familiar with the alternating series, because here it's when we're given a series that has -1 to the n. So if we have the summation of this times a of n, this is a alternating series. So let me just define it. So we can say that this is a series whose terms, so we can say that the terms, they alternate between the English of between, I don't like it, positive, but I can say positive and negative. Yeah, values or reals, right? So I don't want to say integers because integers will limit us. What if we have minus 1 over 2? You say, right? So I don't want the one that will limit us. So we should always try to opt for the ones that won't limit us. So if we have this, now this we can have the series, we can have the types of series. We can have the first one, say n is equals to 1. Then we can have minus 1 to the n of a of n. Then we can have summation n equals to 1 minus 1 n plus 1 of a of n. We can have summation n equals to 1 of minus 1 n minus 1 a of n. You see, right? So we can have any type of sequence. So now we know this, right? So now let's say this. We can let this n equals what? The series of a of n be a decreasing you can let this be a decreasing let's say sequence let me not say the series, let me just put it as the sequence. Right, so real numbers be decreasing sequence, because if I say a series and then a sequence, I'm contradicting myself. So we can say that we let this a of n be a decreasing sequence of positive real numbers, such that the limit as n approaches infinity of a of n should give us 0. You say, right? So this should give us 0. So this will happen. So if we're given this, I think we have two conditions that we can look at. So we have two conditions that we can look at. So the first one is where this converges, right? So we can look at where it converges. So for converges if, so I can say that this converges if first we should have that a of n is greater, so this should be greater or equals to a of n plus 1. And then the second condition, we should look at the limit. The limit will be of a of n, which will be equals to 0, which is this one specified here. Because first we said let this be a decreasing sequence, and for a decreasing sequence we have this, we know this, right? So that's the case for a decreasing sequence. Or I can still write it like this. For a decreasing sequence, we have a decreasing sequence. So I'm just defining that definition. Alright, so this is the condition for convergence. So this will converge if this is the case. So now it means that we can now look at an example. Then I think that the example that we can look at is, let's try to look at some example that is a bit difficult, a little bit difficult, right? So we can say this. We can say, or maybe let's look at the Marathwania. We can look at a bit difficult one. So we can say, let's start with the simple ones. We can say that a of n, maybe a of n is equal to sine n or 1 over n. And then we're told to check whether this is because The reason why I'm looking at this one, but it's fine. Let's start with the simple one, right? We have -1 to the n. We can start with the one that is -1. There are some they don't have -1, right? That's I'm saying that they're a bit difficult. So we can have not a of n. Let me say the summation n equals to 1, because we should be given the summation. Let me say n plus 1. Then we can have cos of 1 over n, right? Then actually this question that I have here, it's an activity in your guide. So already we're going to do a solution for it. So the first condition says that we should have a of n be equals to cos of 1 over n, right? Secondly, we should have a of n plus 1, which should be cos of 1 over n plus 1. You say, right? Then we should have this. Then we check this condition first. A of n plus 1 is less than that. And we know this, that if we want to check that condition, we should start saying this. Okay, let me check. Yeah, it's fine. We should start by saying this. And then, if we have this condition, right, we can say that, let me say, we can do it in two ways. Let me start with by this one. There's also a simpler way. This minus cos of 1 over n. We say, right. So, if we have this condition, we know that, or maybe I can use a P series, right? That's fine. I could use P series, could also be simple, but you're your lecturer. So we know this, a compound thing they're called compound angles. Compound angles, they're like this. Let me just write here. If we have compound angles, we know that cos of 1 over n plus 1 minus cos of 1 over n, this would be equals to cos of 1 over n plus 1, and this sign, it's fine, we'll change there. Then this will be plus sine of 1 over n plus 1 times sine of 1 over n. So this will be times sine of 1 over n, right? This will be, so the question that we can have here is, what is cos of this? So let me check. Yeah, this one will take us a long way, right? If we're dealing with cos, let's just use a P series, because now I'm going to have to use properties. Now you'll be forced to go back to SMTH011. So we can use P series. We can say a of n. So we know that since a of n plus 1 is equal to cos of 1 over n plus 1. By P series, this will be less than cos of 1 over n. Or we just reduce that 1. You say, right? Then, and what is this? A of n. You say, right? And this would imply that a of n plus 1 is less than a of n. You see, right? So this will be the case. Then it means that now we're done checking this. So now we can say, or if the lecturer would require us to do some calculations, right? We can say this. We can say for n greater or equals 1, because we're dealing with positive numbers here, right? We start by taking our a of n. We know that a of n is 1 over n plus 1. And this, we know that this will be less than 1 over n, and this will be less than or equals to 1, right? And then we can have this. If I have this, I can come and put the cos, right? That means that this would be if I come and include cos, this would be cos of, if I would come here and say cos of 0, cos of 1 over n plus 1 less than cos of 1 over n less than cos of 1. Right, but I'm interested in this. You see, right? And this would imply that cos of 1 over n, or I would say this, what is, who can show us what is cos of 1? And we know that cos of this is a of n plus 1, which is equals to cos of 1 over n plus 1 less than cos of 1 over n. And 1 over n, cos of 1 over n is what? A of n. And this will imply that a of n plus 1 is less than a of n. You see, right? Then that will be the case. You can even write it like this. It's fine. So now we check this. Now we can check the limit, right? If we check the limit as n approaches infinity, I was using what today? I was using blue, right? Then if I check the limit as n approaches infinity of, I check the limit of this one, a of n, right? So it means that our a of n is what? A of n is cos of, it's 1 over n, no, not 1 over, yeah, it's 1 over n, like this, right? So yeah, it's 1 over n, a of n. So this would be cos of the limit as n approaches infinity of 1 over n, and this would be cos of, so the limit of 1 over n is what? What is the limit of 1 over n as n approaches infinity? 0. And what is this? 1. What is cos of 0 is 1, right? Ne? So did we get that cos of 0 is 1? No. You see, right? So this would be divergent. So you see, right? So this would be divergent. So do you understand this? So this would be divergent. So it's not always the case that it's gonna converge, right? So let's check the second example. Let's say now I change this and write sine. I change this cos and write sine. So this one diverges. Then number 2, I have the summation n plus 1 sine of 1 over n. Alright? Then I can let a of n be equals to sine of 1 over n and a of n plus 1 be equals to sine of 1 over n plus 1. You see, right? And then here we would now want to check if a of n plus 1 is less than or equals to a of n, to say that it's decreasing, right? So I say that we can use the second condition, this one. We can use this one to say for n, we can say for n greater or equals to 1, we have that this 1 over n plus 1 is less than 0, is greater than 0. Then this will always be the case, and this will be less than or equals to 1, right? So it will be approaching a certain number. So now we're saying that, but usually this one is not that important, right? I'm interested in this. So let's put our focus in this. So let me erase this one, will just be unnecessary, right? And then now we know that from here, I want to now imply that if I was to put the sine of 0 less than the sine of 1 over n plus 1, just introducing this sine 1 over n. Then you know that the sign of 0 will be 0 less than sign of 1 over n plus 1 less than sign of 1 over n. So I'm focused on this. I want to take this. So this now would imply that we know that a of n plus 1 is equal to sine of 1 over n plus 1, and this is less than sine of 1 over n, and this is equal to a of n, which this would imply that a of n plus 1 is less than or equal to a of n. So that is true, right? Then now we can say that therefore we know that a of n is decreasing. So we see that it's decreasing or is decreasing. So now we say that since this is decreasing, now we can come and check the limit now of a of n. Right, of a of n would be equal to the limit as n approaches infinity of sine of 1 over n. This would be the sine of the limit of n approaches infinity of 1 over n, and this would be sine of 0, and sine of 0 is 0. So see that now the two conditions are met. We found that this is correct and this is correct. Then we can deduce now that this converges. Is that right? Then we can say by alternating series test, then by alternating series test, this would mean that the summation of this, right, minus 1 n plus 1 of sine of 1 over n converges. You see, right? Then we are done with the alternating test. So that would be as simple as that. So this is the case. It's simple. It's simple for us to solve this. So it means that now we can go to ratio test. I want us to go to ratio test. Then we can go to ratio test. So any question? But this alternating test, usually it goes with what you call the absolute convergence. So the absolute convergence, or let me share the absolute convergence since they go together. I'll say the absolute convergence. So for the absolute convergence, now remember that always now we're given this. Well, let me just let's say let, or suppose let. Remember we're given this, right? So let's say we're given this, the series of a of n, right? So we can let this be a series. If we let this be a series of real numbers, right? Then we say that if this occurs, the absolute value of this is convergent, and then also the series of a of n is said to be absolute convergent. You see, right? So it is said to be absolute convergent. So this would be a simple scenario. So let's say now we're given an example. Let me check if we can we have an example. Okay, we can use, I think we can use an example. We can try to use this one where we had and from 1 to infinity, and then we had what? Okay, let's say maybe this and plus 1. Let's use that one which we had cos of 1 over n. Yeah, so we had this, right? We did this first one. It was this one. Then we want to check for the absolute convergence, right? Then we want to check if we're given this question, what is it that we can do? So if we're given this, we're going to say let this a of n be equals to minus 1 and plus 1 cos of, I think this will be cos of 1 over n, and also the absolute value of this to be minus 1 and plus 1 cos of 1 over n, and this will be equals to cos of 1 over n. Right? That means that now we can check this. Does this converge or diverge? Let's say, right? So it means that now we can check. This would imply that absolute value of so we can tell us, does this converge or diverge? We can tell us, does this converge or diverge? Does this converge or diverge? Will this converge or diverge? So in order to, I think I have a calculator. Let me check. If we have cos of 1 over 1, so be 0.54, 0.87, 0.94, 0.96, 0.98. Yeah. So would this converge or diverge? Anyone? Would this converge or diverge? It's a homework to go look at this. Go check this. Use any type of test. You see that any question can come. You must use any type of test to check whether does it converge or diverge. So use that. Should be your homework to look at. Alright. Or it diverge. Okay, someone is saying it diverge. So thank you. Now, but it's a homework for you guys to look at. If this diverge, therefore this would also diverge. You see, right? And then, but previously we saw that this one did diverge, right? So you can try to check. But I just want you to know, how do I check that this one diverge or converge? So now let's go to, we can go to ratio test. So we can go to ratio test. Yeah, without any waste of time. Without any waste of kululu. The kululu, the time. The conditional. So let me write here, right? Absolute convergence, conditional convergence. So we won't do the conditional one. I didn't check it out, right? So I forgot this one. I forgot to check it out. So I'll check it out. The next class we're gonna touch this one. So now we come to ratio test. After ratio test, it's a root test. Then we can, I think we have 30 minutes left, right? We can conclude after that. And then we see what is it that we are left with. So we can, I think what is the other word for the root test? Okay, maybe the other word for the what's this? Yes, I think yes, the root test. What is the other word for the root test? We call the root test what? They can come and bring it as the other way, right? The other word. So let me just type here. The ratio test is to read this word. Another word for the ratio test is this. For the ratio test is the D'Alembert. That's what test. So these guys are crazy, isn't it? You must just know that this word means what. We're talking about a root test. As I did send it on there. Okay, let me write it here. That's fine. It's D'Alembert. Yeah, I think it's D'Alembert test. Yeah, D'Alembert test. So that is another word for the ratio test. So they can try it. So we see when they want people to get total, then they bring such words. They're there on the guide, so they won't be wrong. Alright. These words are there on the guide. And another word for the root test is the nth test. Right? So I think for the root test, but we'll confirm that. So when you come to ratio test, things become simple now because some of the things we've been doing them before, right? We've been doing some of the things, so it will be simple for us to complete the root test. Lambert's test, yeah. So it will be simple. So here we're gonna look at two conditions, right? So the first condition would be if we have a limit, right, and that limit is less than 1. So this would mean then the summation from 1 to infinity of a of n converges. So we'll check how do we find this limit. The question is, how do we find this limit? Then I said that if L is greater than 1, then the summation from of n from 1 to infinity of a of n diverges. You see, right? Now the question is, how do I check this? Right? How do we find this? So let's assume we're given this, right? So I believe they can bring such questions on the tutorial. Let's say we're given this. We are given the summation from n to 1 to infinity, from n equals 1 to infinity of they say this say 2n ratio, then they square it, right? Say all over, then we have 4n, then we have ratio, right? Then they say for all n greater or equals 1. Now for all n element, but I've already written that. There's no need. We know what is n. So let's say we're given this. Let's say they want us to check whether this thing converges or diverges. So for the ratio test, we need this. We need to let a of n be equals to this And then we have our a of n plus 1. So a of n will be equals to 2n plus 1 so this will be 4n plus 1. Yeah, I think this will be fine. So yeah, so if we have this, right, now we need to check a of n over your a of n plus 1 over a of n, right? So we need to compute this. Then after computing this, at the end we're going to take the limit of this, right? So first we have this, the numerator is going to be 2n plus 2 factorial squared. Then this will be, the denominator will be 4n plus 4 this, and this will be divided by a of n is, so I always write it the same way I'm writing it. You say we put the divide like that, it's gonna save you time. Squared all over 4n factorial. Now the next thing to do is to expand this, right? So we can say this one, we can expand it like this. We can say okay, one thing we have to factor out, yeah, it's fine. I think I'll factor out can I factor out 2? Let me see. That's fine. But the simplest way to do this would be to change this. So you should check the steps, right, without having to think. I think I'll think about factoring later, right, and other steps later. The second thing to do is to change this division to multiplication. Then that will tell me now what is it that I need to do. So I need to cancel everything that is a factorial. So for me to cancel them, I need to do something. And the question is, what is that thing that I need to do? 2n factorial squared. So I check. I need to either cancel this and this. You see, those are the like ones. You see, those they look alike. So for me to do that, I can start by reducing the inside. The inside, it says this. It says here I can start by doing this, 2n plus 2 factorial, and also here 2n plus 2 factorial. I can start by removing that squared, right? Let's start by removing that squared. Then this one is 4n plus 4 factorial. Then I'll reduce them. Well, let me start by reducing this denominator, because this one we know that we should reduce it to this. You see, right? So this can be 4 plus 3, 4n plus 2. Hey, why am I writing plus here? 4n plus 1, then 4n factorial. You see, right? I was just reducing that one unit at a time. Then I say multiply by 4n factorial all over 2n factorial. So this is squared, right? Then times 2n factorial. You see? Then this would be, then these ones here, I can reduce them like this, 2n, because I know that I need to reduce them to 2n factorial, right? I can just reduce them like this, 2n plus 2, 2n plus 1, and then 2n, I stop at factorial. Then I come again and reduce the other one, 2n plus 2, 2n plus 1, and this one, keep in mind, this will cancel, right? 2n plus 1, then 2n factorial all over, then I combine this down here also, 4n plus 3, 4n plus 2 4n plus 1. Then I combine the ones down here. 2n factorial times 2n factorial. Then this also would cancel. So anything that is a factorial, I'm cancelling out. You see, right? Anything that is a factorial, I'm cancelling it out. So here I will be left with, these ones without a factorial. 2n plus 2, 2n plus 1, 2n plus 2, 2n plus 1. All over. Then here I'll be left with 4n plus 3, 4n plus 2, 4n plus 1. So if we check this, I would let me check which one can I try to factor out here. Did I leave anything out here? 4n. Let me see, this one was 4n. Oh, I forgot this here, because the other one is 4n plus 4. Yeah, it started from 4. So I must keep on adding it here. N plus 4 and 4n plus 4. Right? Then this would be, if I check this one here, on the numerator I have 2n plus 2. So I can factor out 2 there. Then I'll be left with 2n plus 1. Not 2n plus 1, man. I'll be left with n plus 1. N plus 1. Then this one 2n plus 1. Then this one I'll also factor out 2n plus 1. 2n plus 1. So this 2n plus 1 would be, I can square this, right? But it's fine. I'll just write here 2n plus 1. So this would be all over. This I can factor out any number, right? Which is, I can factor out, let me see, which one can I factor out here? But I want to cancel 2. It's fine, I can factor out 2. Yeah. So, or 4, it's fine. Also 4 would be fine to factor out. 4 n plus 1. Yeah, 4 will be fine, because it will cancel some things. 4n plus 3. Then this one will factor out 2. And 2n plus 1. Then 4n plus 1. Then I check the ones that cancel. 2 would cancel 2. 2n would cancel 2n. N plus 1 cancel n plus 1. And then these 2 would be cancelled with 1, 2 here. We'll be left with 2 there. So this would be n plus 1 times 2n plus 1 all over, and here would have 2 4n plus 3 4n plus 1, and this would be 2n squared plus this would be is it 6n? Let me check. 2n plus this would be what? 3n. Yeah, it won't be 2n plus n, it's 3n, not 6. 3n plus 1 all over, and this would be let's calculate this. 4 by 4 is 16, and then n squared plus this would be 15. 4 by this would be plus 4n plus 12n plus 3. This will be 16n squared plus this will be 16n plus 3. Yeah. And this will be 16n squared plus 16n plus 3. And this would be 2. Well, let me take out 1 over 2. Oh, but that's fine. Now let's find the limit for this. The limit for n approaches infinity of a of n plus 1 over a of n would be equals to the limit as n approaches infinity over 2n squared plus 3n plus 1, which will be all over. So I can take out this 1 over 2, right? Because there's 1 over 2 in the denominator. Then I'll have 16n squared plus 16n plus 3. And this will be 1 over 2. The limit of this, if I take out this, right, if I have the limit as n approaches, and let me just show it, I have n squared 2 plus 3 over n plus 1 over n squared. And this will be all over n squared 16 plus 16 over n plus 3 over n squared. Then this would be equals to 1 over 2 times the limit as n approaches infinity over 2 plus 3 over n plus 1 over n squared all over 16 plus 16 over n plus 3 over n squared. And this will be 1 over 2 times 2 plus 0 over 16 plus 0 plus 0. And this will be 1 over 2 times 1 over 8, which this will be 1 over 16. Or I would say 1 over 16. Given that this 2 will cancel this 2. You see, right? So we got 1 over 16. Then we go back. We got 1 over 16. Is 1 over 16 less than 1? Yes. Then what will happen to the series? It will converge. You see, right? So let's go and conclude now. For conclusion, we're going to say since, well, let's not 0 man, less than 1, right? Say that since the limit as n approaches infinity of a of n plus 1 over a of n is less than 1, I can say then the summation of n equals 1 of what's that equation, 2n summation squared 4n summation will converges. You see, right? So this will converge. So let me give you this as an exercise to do. So let me say try. The first one will be the summation n from 1 to infinity of n squared e to the minus n plus 1. Try this. Then again, try summation infinity n equals 1 of 1 over n squared. Let me just write here. C. Try this. For C, try the summation n equals 1 to infinity of n to the 7 over 2 to the n. And then for d, you can try the summation infinity n equals 1. You can see 2 to the n over n to the third n plus 4. So some of them they look kind of simple up until you do them, right? That's why I'm giving them to you to go try them. So now we can look at I think we can look at a root test. So if we can look at the root test, we can be able to deduce this. So any question, a root test, then we close. Any question? No. Here, let me give you the last one. E to infinity. I can say this one is similar to the one which we're doing, right? We can see. Yeah, I'm not gonna give you difficult things. I won't give you difficult things. I'll just give you things that are similar to what we did, right? Yeah. So if you can do this, trust me, the tutorial is gonna come in somehow like this. So if you can be able to complete such questions, yeah, you are dangerous. If you can complete such questions, you're dangerous. Trust me. You are ready, evil, not just dangerous. You are ready. Yeah, you see, A, F, E. Let me even underline them. I'm gonna underline F, E, A, and yeah, these ones that they fall under what we're just doing here. So B, C, those are simple. C is bit, simple also. But yeah, it might require you to use Pascal's rule, but yeah, we'll see if you can come up with another thing. But you know, from mathematical induction, you had something like this. You can come up with. I'm not saying you should use mathematical induction. I'm just saying you had to do something. So you can, as long as you know how to expand that, it's gonna be simple for you. So yeah, let's do the any question before I can say. Okay, seems like there's no question. Let's do the ratio test, the root test. So yeah, we have like 7 minutes left. At least we pushed guys. Root test. So this is a sign. Saturday we are beginning with we are starting with what's that power series right here. It's one of the nicest topic. So we're saying that for the ratio test, right? For the root test, let's say we let I let let's say a of n, not really a of n because it's a root test. I'll let the limit as n approaches infinity of we need. So this is called the nth. So I want you to understand this, right? It's called the nth root test. Don't forget this n. Most forget this n, that's why I'm writing it there. So it's bit combined with that's why I did the absolute convergence. So it's bit combined with the absolute convergence. And then if this is the case, I think also this pen is tired of writing, you see. Now it's writing things. Then we can say the series if that is the case, Then this series, we can say this. If this is the case, first one, we can say it converges. All right. What does it converges to? So it converges absolutely It converges absolutely if L is less than 1. So still the same condition as that one of root test, the ratio test, right? Still the same one. Then also it diverges if L is greater than 1, right? Then we say that if, also I think I forgot one condition here. Then if L is equals to 1, the test fails. You find that L is equals to 1, the test will fail, right? So also here, if L is equals to 1, the test fails. And the most boring part about these ones is that you choose it. When you get there, realize, no man, ish, you got one. It's another thing. Now you must start, because if the test fails, right, and I'm using this test, if the test fails, it means that I must use an alternative test. You see, not if I'm saying alternative, you'll think I'm talking about the test. You must use another test. You see, so that's the problem. That's the only disadvantage that we can face here. You see, finally you apply a root test, waste your time. Maybe do it for, you saw that question is too long, like this one. Maybe do it for like 10 minutes. You find that it's equals to 1, so the root test fails, or the ratio test fails. You see. So every time you come across a question with what's this question? What do you call this? Factorials, right? You should apply root test first, not root man ratio issue. Why am I always saying root? Should always apply a ratio test if you come across such a thing. So now let's say we're given a question, right? And then this question they say that we're given the summation. So this will be the summation from 1 up until infinity. Let's say something like this we're given, but we change this, right? We can swap with those. I think we can make it to be like this. I think it can be something like that, but let's not make it to be that. Can say what? Let me just take that one. N to the 7 over, was it 2 to the n? 2 to the n. Alright, so let's say we have something like this, at least, but do you see I want to apply the root test, so you must do that one using the ratio test. So if I have this, so I'm going to let a of n be equals to n to the 7 over 2 to the n, such that the absolute value, let's start with the n absolute value of a of n will be equals to n absolute value of n to the 7 over 2 to the n. Then this will remain positive, right? So this would be equal, so this would imply that this would have would do this separately, then this one would be 2 to the n. You see, right? And then this would be, we're allowed to say this. So we can take out the this, we can put it outside. Then we'll have here 2. You see, right? So this would be, now I must come and apply the limit. So if I come and apply the limit as n approaches infinity of this, then the limit would be, this would be, so what is the limit of this, or for the one on the numerator? We can tell us what is the limit for that. So let's check it out. Let's check what is the limit for that. The limit, let me check it here. Limit as n approaches infinity of n to the 1 over n. This will be equals to, so this will be e 1 over n ln n, and then this would be equals, I must put the e which is infinity of 1 over n ln n. So this will be equals to e limit which is infinity of ln n over n. This would be e. So if I plug any bigger number here on ln n, you see, if I plug ln of infinity, if I plug infinity there, let's check. Let's say I'm going to plug 500. I'll get a smaller number, 5,000. I get a smaller, it will always be a smaller number. So it means that the denominator will always be bigger than the numerator. So this would be 0. And this is 1. You see, every time I come across this situation, just say is equals to 1. So I just wanted to show you that that is 1. So this would be 1 over 2. You see, right? And this 1 over 2 is less than 1. You see, right? So we can say, thus, the series converges by the nth root test. You see, it converges what? Absolutely. So I've already shown those absolute values there. So you can just write it converges. So this would be the case. Any question on the root test? Any question on the root test? Or just to maybe we don't get penalized, right? We can, because I don't want us to be stubborn, right? You can just include the absolute part. Yeah, the series. Okay. So I can say that the series is absolute. Or maybe absolutely converges. Converges by, yeah. Yeah. The series absolutely converges by the nth root test. Any question? Any question? So if there's no question, we can call it a day. So for this one, I'll send you questions also. Let me just write here and say try. Let me just say try. Let's try what? That's fine, you can try this one. I'll try to find the ones that